रोहित, आवाज
ओके।
आ रही है?
यस सर, यस।
ठीक है जी। रोहित जी, डॉक्टर साहब ने ज्वाइन कर लिया, उनको को होस्ट बनाइए आप। डॉक्टर देवाशीष जी ज्वाइन कर लिया है सर ने, आप को होस्ट बनाइए। उनका नाम ये है, डॉक्टर देवाशीष। IRI न्यू दिल्ली भी करेंगे तो आ जाएगा सर्च। डॉक्टर साहब, गुड इवनिंग, नमस्कार। डॉक्टर साहब सुन पा रहे हैं आप मुझे, देवाशीष सर?
Am I audible?
यस डॉक्टर साहब, नमस्कार।
नमस्कार नमस्कार
डॉक्टर
नमस्कार।
साहब बस 2 मिनट्स में स्टार्ट करते हैं।
हाँ, बस हमको स्क्रीन शेयर करने का ऑप्शन दे देना, उसके बाद।
बिल्कुल डॉक्टर साहब, सब स्क्रीन का सबका आपको ऑप्शन मिल जाएगा। ठीक है।
श्योर श्योर श्योर
जी,
श्योर।
आप प्लीज करिए एक बार पीपीटी अपनी शेयर करके देखिए, पीपीटी।
हाँ, एक बार पीपीटी में शेयर करता हूँ। ये है स्क्रीन। वही भी एक। इज इट विजिबल?
अभी नहीं डॉक्टर साहब, उस अभी नहीं हुआ, विजिबल नहीं है।
सर पीपीटी ओपन करिए, स्क्रीन दिख रही है
पीपीटी
आपकी।
ओपन करिए, आप स्क्रीन दिख रहा है आपका बहुत अच्छे से।
ओके।
डॉक्टर नंदिनी, आप हैं मीटिंग में?
जी सर, मैं यही हूँ।
ठीक है, थैंक यू।
नाउ इज इट विजिबल?
यस सर, एक बार पीपीटी मोड में करेंगे सर आप इसको प्लीज। हाँ, एक दो स्लाइड मूव करेंगे सर, या इट्स मूविंग। डन 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 सर।
डन 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 सर, डन सर।
ओके
फर्स्ट स्लाइड कर लीजिए सर, फर्स्ट स्लाइड। हाँ,
ओके ओके।
ओके। सर सिर्फ 2 मिनट का समय दीजिएगा प्लीज, बस 2 मिनट में हम स्टार्ट करते हैं सर।
ओके ओके। आई एम इन द डिपार्टमेंट, सो नो नो हरी। हम कर सकते कंटिन्यू बहुत टाइम तक।
नंदिनी जी, यूट्यूब और जूम को मिला के आई थिंक 450+ कैंडिडेट ज्वाइन कर चुके हैं। नंदिनी, आप सुन पा रहे हैं मुझे?
हाँ जी सर।
अब आप स्टार्ट करिए।
So good evening everyone. A very warm welcome to all the participants for joining us for day 7 of International Agriculture Workshop from Training. Mati 2025, proudly organized by AgriMeet Foundation Bharat. I'm Nandini Sharma from AgriMeet Foundation Bharat. And this Mati 2025 is jointly organized by AgriMeet Foundation and in collaboration with our esteemed national and international partners. Before we begin, I want to remind everyone that Mati 2025 is not just a 10-day program, it is a transformative journey where each day brings the finest scientific minds of the country to give and guide us towards sustainable, modern, and future ready soil management. Every session strengthens our understanding of soil health, precision approaches, climate resilience, digital agriculture, and regenerative technologies. And today, day 7 feels truly special. It is my utmost honor, privilege, and heartfelt pleasure to welcome a scientist whose work speaks and whose work has not only advanced soil science but has protected human health, strengthened policies, understanding, and revolutionized how we assess contaminated soils. Please join me in welcoming Dr. Debashish Sir, Scientist of Soil Science, ICR, New Delhi. Sir, we are genuinely humbled to have you with us today, and your presence adds extraordinary value to Marti 2025, and we feel privileged that you choose to share your expertise with our participants. And I want to tell the participants that Sir is India's most respected young soil scientist, widely known for his outstanding work in risk assessment and remediation of metal and metalloids polluted soils. He completed both his master's and PhD from ICR IRI, New Delhi, one of the most prestigious agricultural research institutions in the country. His groundbreaking contributions include developing a risk assessment protocol for metal polluted soils using an advanced modeling framework, establishing safe limits of extractable metals and metalloids in soil with direct implications for human health protection, receiving the highly prestigious core research grant from the Department of Science and Technology, Government of India. He has over 50 peer reviewed research publications in top international journals, reflecting his strong scientific foundation and global impact as well. His excellence has been recognized with several prestigious awards: Fulbright Nehru Postdoctoral Research Fellowship, ISCA Young Scientist Award Golden Jubilee Commemoration, Young Scientist Award of ISSS, IRI Merit Medal for Outstanding Research Contributions. His clarity of thought, scientific rigor, and commitment towards environmental safety make him one of the most inspiring figures for today's young researchers and scholars. We are sincerely honored, sir, to welcome you to the day 7 of Marti 2025. Thank you for gracing this program. With your presence, we eagerly look forward to learning from your expertise today. Thank you for joining with us. Over to you. The session is yours.
Okay, thank you, Nandini. So, first of all, thank you so much for inviting me and presenting our work. So far, actually, for last 10-15 years, actually, we are working in the Department of Soil Science and Agricultural Chemistry. Am I audible? Just can you just confirm? Is
Yes, sir, you're
Yes,
audible.
Dr.
Completely
Yes, Dr.
Okay, so we are working in this field and particularly risk assessment, because all will talk and for last 7 days actually you are actually learning so many things, especially on soil health and other nutrient aspects. But this field actually, the soil pollution, this is actually kind of burning issues not only in India but across the world. Soil pollution, basically, we are actually working mainly on metal and metalloid, but there are many ways that can harm soil, like your pesticides, say pesticide pollution, then other emerging contaminants recently actually came into the figure, like pollution of soil with microplastics, nanoplastics, then your kind of organic pollutants, example like PFAS. So these are kind of emerging pollutants. But basically, we are working on metal and metalloids, and I will try to give some glimpses what work actually we have done so far and what management, how we can manage these pollutants in soil so that it will not enter into our food chain, because that is our ultimate stakeholder. Human being is our ultimate stakeholder. Obviously, animals are also there, and we all know that One Health concept, the government of India now is promoting One Health concept. So whatever we are consuming, that should be free from any toxic metals or metalloids. And so moving forward, I think for last 7 days, all dear participants, all of you know the definition of soil. So am I, is it visible? I'm just moving to my second slide. Is it visible? Just confirming.
Yes, sir.
Okay.
Yes.
So all of you know, but if students are there, particularly for you, you should know the definition of soil. So you all know it's a natural body and comprised of solid, liquid, and gas that occurs on the land surface and occupies space. Now, our interest is pollution. So there are two terms, pollution and contamination. Now, you should know the difference between pollution and contamination, because these two terms are frequently used, but we should be very much careful what term we should use. So pollution means that already the damage to human health, animal health, or the biological system that already took place. So there is no question that whether it will affect in future or not. So that is actually pollution. Whereas the contamination is that the beginning. So later it may be converted to polluted soil, or if you take some measurement or some management strategy, then that soil you can stop at that particular point. So that is actually contamination. So contamination is actually starting towards pollution, and pollution is actually the final destination. So in one line, actually, we can say that all polluted soils are contaminated, but all contaminated soils are not polluted. Okay. So this is actually very rudimentary terminology. So you should know about the difference between pollution and contamination. And now moving towards like definition of metal from chemistry, actually in 11 and 12th standard chemistry, we all know that definition of metal, it can be defined as metal having specific gravity, which is having more than 5 specific gravity and having atomic number more than 20. So above calcium in periodic table, all can be classified as metal. Whereas metalloid, if we take example of metalloid, in terms of properties, we can differentiate the properties of metalloid actually in between metal and non-metal. Okay, metal, the properties we all know that it is a good carrier of heat as well as electricity, whereas non-metal, it's a poor conductor of heat and electricity. So metalloid, the property, it lies in between metal and non-metal. And example in today's lecture, I will give you example of arsenic, selenium. These are actually example of metalloids. But so far, actually, we have done work on arsenic, particularly in West Bengal, where the pollution actually exists. I will show you some on-field data where actually we conducted some field survey. Pollution of arsenic, particularly in groundwater, as well as in soil, as well as in your rice crop, then in human health, particularly. Some work we have done with the help of medical personalities, and that I will present you later. So this is definition of metal and metalloid, and we started with pollution and contamination. Okay, so today we will mainly, again I am repeating, today we will mainly focus on the inorganic contaminants, and that is actually metal and metalloid. So, okay, regarding question answer, just Nandini, can you just confirm whether
आपके लेक्चर के बाद में 5 मिनट का डाउट क्लियरिंग सेशन रखेंगे सर.
Okay, no problem. but
हाँ जी
I
इन
usually
बिटवीन नहीं
prefer.
करते सर हाँ जी जी
Okay,
जी
okay,
सर
in between. Okay, okay. So now coming to different sources. Now we have already placed the topic in your table. Now let's start with the different sources of metals and metalloids and the affected areas. So you should know. I think if someone, if you have any preliminary knowledge, then also I should tell that what are the different sources of metals and metalloids in soil and as well as the affected areas in India particularly. Now, I will start with arsenic. You know, this data actually somehow you can modify because recently we have published one article in 2023 where we have seen that more than 250 million people in more than 50 countries are probably affected by arsenic poisoning through drinking water. We have published that work. So you can see the gravity of this problem of arsenic worldwide, not only in India, but across the globe also this arsenic problem actually identified, particularly in groundwater and more favorably in drinking water. This problem actually reported. Now in India, with respect to India actually, this problem long back in 1980, problem actually was identified, particularly in Indo-Gangetic belt, and most affected state is actually West Bengal. And other parts are also there like your Bihar, some parts of UP, Western UP. So these are actually area where arsenic reports are there in groundwater, and in from groundwater to soil actually it comes through irrigation water, and from soil to your rice crop, mainly rice crop. It is actually most favorable uptake of this element was seen by rice crop. So I will tell you later. Now in India, this is the problem of this arsenic is actually geogenic. Now what is geogenic origin? Geogenic means the origin, and there is another term that is anthropogenic. Anthropogenic means that is man-made problem. So we are using wrong thing like your application of say sewage water, industrial effluents to our agricultural land. Then that problem may be aggravated, but that that will come with respect to other elements like your lead, cadmium. Those are actually problem associated with anthropogenic related. But this arsenic problem is actually through geogenic. That means it is already present in the groundwater, either in different complexes, and that's why I have pointed out here reasons for arsenic poisoning in groundwater. It is there are two hypotheses like your arsenopyrite oxidation and ferric oxyhydroxide reduction. So due to oxidation of arsenopyrite, there is mineral As FeAS2, that mineral, that oxidation of that mineral, that actually causes the release of your arsenic, and sometimes reduction of ferric oxyhydroxide, where arsenic is actually bound. If reduction takes place, then also arsenic can be released from that mineral. So out of these two hypotheses, this hypothesis 2, that is ferric oxyhydroxide reduction, is widely accepted reason for arsenic poisoning in groundwater. So you should correlate that from where it is coming. So arsenic main source is actually geogenic. That means it is already present in the sediments or in the groundwater, and through application of irrigation water during cultivation, that arsenic may come from that water to your agricultural land, and from agricultural land to ultimately crops, and from crop to your food chain like your eating material, rice, whatever we are actually consuming. There is one diagram, later I will show you. Now next, this is what actually I was talking, that Indo-Gangetic belt, where the reports from time to time actually people have reported, and now extensively work already have done. So many literatures you will see on arsenic problem. with respect to, particularly with respect to West Bengal. And recent few works actually you will see with respect to states like Bihar, say UP also, and recently we have also published one article for Bihar also in agricultural research. So that area is also affected. So why I am showing you this will give you idea that where this problem actually exists, and the Indo-Gangetic belt, the productive belt, where actually some reports where rice crop where people grow, there actually reports are there of arsenic contamination. This is what I told you, like the problem is mainly confined to your West Bengal, and these are the area. Mainly 5 districts of West Bengal reports are there with respect to arsenic problem, particularly in groundwater as well as in soil as well as in crops. The arsenic problems are there, and the 5 districts are Nadia, North and South 24 Parganas, then Malda, Murshidabad. These are actually area where actually this arsenic problem exists. Now, next, with respect to arsenic, we just introduced that the areas and the reason for arsenic problem in the food chain. Now, moving to selenium. Selenium is another example of metalloid, and this is also geogenic driven problem. So the problem so far reported in Punjab, some pockets of Punjab, and sub-Himalayan West Bengal, Assam and Meghalaya in some parts. In discrete areas actually selenium problems actually reported, and mostly the parent material is actually mainly upper Sibalic rocks, mainly composed of polymictic conglomerates that are actually bearing material for this selenium. So selenium and arsenic, these two are example of your metalloids and that are of geogenic origin. Okay. Next is chromium. The problem of chromium is actually in soil. It is actually related to anthropogenic. And what I told that anthropogenic means that is man-made, and geogenic means it is already present either in sediments or in groundwater or through parent materials. It can cause the pollution in the soil plant human continuum. But chromium, with respect to chromium, the problem is actually man-made. And most of you know that the tannery effluents, due to application of tannery effluents, particularly when the tannery industry, they discharge their effluents to say any water bodies, particularly say river water, then the problem of this chromium actually it's diversified from that groundwater, from that river water to ultimately agricultural land. If irrigation was there, then this problem will be aggravated. Okay, so some database like about 3,000 tanneries are there in India, and the quantity of this, you see the amount of water required for processing of 1 kg of skin, around 30 to 40 liter of water is required. Okay, and the chrome tan liquor contains, this is one estimate that about 97 to 5,125 ppm of chromium can be present in chrome tan liquors. Okay, so some areas if we see like arsenic, we discussed that arsenic problem mainly in West Bengal and Indo-Gangetic plain. Selenium problem mostly in your Punjab seleniferous soil, and chromium problem, some examples I have written here like Jajmau tanneries near Kanpur, then river Palar in North Arcot district of Tamil Nadu, then tanneries in Periyar discharge particularly in Tamil Nadu because of the discharge of the chromium rich effluent into Kaveri river. So these are some areas actually, and we have also in our department one work actually conducted recently in Kanpur area where reports actually we have seen that the buildup of chromium in soil also. Now with respect to cadmium, zinc and lead, because not all elements in periodic table after calcium will not be taken into account, because the transfer is very important, because if it is present in soil and it is not getting entry like into the food chain through plants, then it is okay. Otherwise your the element will be treated as like this is very serious issues. So cadmium, zinc and lead another examples of your anthropogenic related issues, where actually this is also man-made problem, where application of say industrial effluents or say sewage water or any waste water of domestic origin, that if that use for your irrigation purpose, then the problem of this cadmium, zinc and lead can be seen. And the areas actually I will show you. The story actually started with your Jinstu Valley for cadmium, where Itai disease actually was first reported due to cadmium uptake by rice crop there, and followed by people actually eaten that rice contaminated with cadmium, and then later they discovered that this is a problem of cadmium. And here in India particularly, zinc, cadmium, lead, these are actually related to your industrial effluents mostly, and sometimes sewage effluents also. In India, we have conducted one work, particularly in your Debari region of Rajasthan, one zinc smelter effluent. We have seen there that the zinc smelter factory was there few times back in Debari region, where due to continuous application of zinc smelter effluents, we have seen the buildup of zinc as well as cadmium as well as lead. And some areas of your say Sonipat, where cycle factory, due to application of your cycle factory effluents, we have also seen the buildup of your cadmium as well as nickel. That is another example of your anthropogenic related problem, nickel pollution in soil. So these are some data actually. So far we have seen that contamination of different elements in different areas. So far the area, if we talk about areas of contamination, so map, you cannot see the map of this contamination. So that is one area of research researchers should take. Try to establish the map of say arsenic pollution or nickel pollution, lead pollution, because in this data actually this table, these are actually discrete area, like this area is affected, this area is affected with respect to this element. So if anybody try to create some map, then that would be of great value, that information. So that thing also we can think about. So here I have taken example of say Malda, where I have reported the arsenic concentration in soil as 6.7 ppm, say for example. And here another example. So these are the area, Mitrapur, Nadia, already we have discussed. Rajasthan with respect to say nickel, lead and cadmium. Then Keshapur sewage effluent plant. In Delhi also some areas like your sewage effluent irrigated area of Keshapur or say Madanpur Khadar, or say other areas where sewage effluents, farmers use actually sewage effluent for their irrigation of crops. There we have seen the buildup of heavy metals like lead, cadmium and nickel. Now, so far this is actually first part of my lecture, that areas as well as cause of contamination for different elements. Now again I just summarize the thing actually what I talked. So far we have discussed that arsenic problem, that is geogenic in nature, and the problem is mainly confined in Indo-Gangetic plain. Then we have talked about selenium. Selenium, the problem is actually again it is geogenic, and the problem is mainly confined particularly in Punjab area. Then we talked about chromium. where it is again anthropogenic related problem and mainly due to discharge of your tannery effluents to your irrigation channel like your river water or any other sources, that actually causes the problem of chromium in soil. Then we talked about your nickel, then lead and cadmium and zinc. Particularly these four elements, these are actually again anthropogenic related problem because of application of industrial effluents like your zinc smelter effluents or industrial effluents, other industrial effluents or your sewage effluents, particularly in Delhi belt, where farmers actually use the sewage effluents, and ultimately we have seen the buildup of your cadmium, lead or nickel in soil. Okay, so these are all present in soil. So far we have discussed that these are the pollutants that can be present, and because of application of either wastewater or your industrial effluents or your contaminated groundwater. Okay, now we need to monitor, either you need to monitor or assess that how much quantity of your heavy metals or your metalloids are actually coming, and the level of buildup, that is very important. Okay, because uh, we are actually conducting here another experiment, application of sludge in soil. Sludge, it is actually after processing of sewage effluent, the solid material is known as sludge. So sludge, it has some good value, good properties like your carbon content, nitrogen content, phosphorus content, potassium content, and other elements like your micronutrients, all are present. But at the same time, in sludge also, there are reports of presence of trace toxic metals like your cadmium, lead, nickel. So we have to use the material judiciously so that all can be managed, because we are in a single sphere where all are actually linked, because food crops we usually grow in soil and with the help of irrigation water. So water, then your water, then your soil, then from soil to plant, and from plant to human food chain. So these are actually connected, okay, under one health. So we need to actually assess. My main message to all of you, that we need to assess the polluted soil. If there are reports, if you are getting previous information that these areas are actually affected with some pollutants, then assessment is required, as well as your monitoring of polluted soils. How we can go for assessment and monitoring, I will tell you. Here are some questions for you. Is it necessary to monitor pollutants? And if we don't monitor, then what will happen? And how we can assess and monitor the pollution? So in the next coming slides, actually, we will discuss all these aspects. Now, why we should need to monitor these pollutants? So far, we have discussed that the sources of pollutants is mainly under two categories: geogenic and anthropogenic. And anthropogenic examples we have already discussed, that application of sewage water, industrial waste, industrial effluents, municipal solid waste. So these are actually cause of your source. Already we have discussed. Now, why we need to monitor? Because transfer of the potentially toxic metals or metalloids to human and animal food chain, this is actually concerned. Okay, if your say daily food is contaminated with your pollutants, then for long term consumption will give you some negative results. Obviously it will give you some negative results, either through some health deformities or health effects or health outbreak, that you will see. In the coming slides, I will see you what are the different negative effects of heavy metals in human health. So transfer of these potentially toxic metals to human and animal food chain, which ultimately resulted into various diseases. So that is our concern. And another important aspects actually we are overlooking is that in most countries the total metal is used as an index of hazard. Okay, if you see the research article, most of the research papers related to your metal and metalloid pollutions, they use their standards as total metal. But for last 10 years, actually, our research team actually changed this concept that total metal is actually not actually protecting. If you take example of total metal for your comparison, then that will not actually protect the human health. And what will actually protect you, that is actually extractable metals. So we need the safe level of extractable metal that is actually missing, okay, not only in India but across the globe. So we have tried to set or to fix the safe level of extractable metal and metalloids in order to protect human health as well as animal health. So that I will show you how we have done, how we have fixed these safe limits. So this is the reason of monitoring as well as assessing the polluted areas. Okay. Now, impact, what actually I was talking, that what are the bad or the negative impacts of these pollutants towards the human health. So taking example of arsenic, we have done field work where in arsenic affected, we have seen the arsenic affected people there, and we have seen the disease burden also. What are the different disease actually caused due to long-term consumption of your arsenic contaminated water? Say for example, due to prolonged arsenic exposure, one can expect skin cancer, hyperkeratosis, hyperpigmentation, then black foot. So these are few diseases actually I have listed. There are so many health outcome are there due to long-term exposure of arsenic, either through drinking water or through your contaminated rice. Then selenium, the problem of selenium, if you see the impact on human health, loss of hair, nail deformities, selenosis, interferes with reproduction. These are some outbreaks. Then chromium, renal dysfunction, lung cancer, then your cadmium, Itai disease. So these are some outcome actually due to long-term exposure of these pollutants towards human health. Now, how we can do this assessment and monitoring? So I have listed the techniques. These are the techniques. If you apply these techniques, then you can assess your pollutants in particular agricultural land. So few advanced techniques. So far in literature, you will see that the assessment may be limited only for estimation of your say total heavy metals or metalloids, or maximum your available estimation of your available metals or metalloids. But we have done few research on how we can advance our thoughts or techniques that we can assess the heavy metals and metalloids, particularly in polluted soils. By applying that knowledge, actually we will be able to successfully manage the risk of polluted soils, okay, in order to, because our ultimate aim is to protect the human health. So for that we need some accurate or the precise estimation of your heavy metals or metalloids in soil. So few list I have listed here, total or trace toxic element extraction, then extraction of soil with some chelates or salt. This is the very common method, extraction of soil with chelates and salt. By applying that, you will be able to know the level of your heavy metals or metalloids. Okay. Then your total trace toxic element extraction, how we can do total elements, that we can do with the help of acid digestion of soil with your acid, particularly either diacid you can use or triacid mixture, nitric acid, perchloric acid, sulfuric acid. Okay. Or one method is there, that is your aqua regia extraction. With that also we can have the picture of total trace toxic element. and extraction of soil with chelates and salts. Examples, we all know that DTPA soil test. With the help of DTPA, we can estimate said cadmium or lead. Other chelates examples like your EDTA. EDTA is also used for extraction of soil, okay, for estimation of heavy metals. Then salt, example of salts like say calcium chloride, calcium nitrate. These are the salts that can be used for estimation or the assessment of your level of pollutants. That is important. Now, what are the advancement we have made? We have tried to extract the soil solution extraction, and 1:2, 1:5 soil solution extraction, leachate collection, TCLP. This is another example of your advancement of managing the polluted soil. Toxicity characteristics, leaching procedure that can also be used, and extraction with some buffer agents. Okay, so these are few examples of your advanced techniques by which we can more accurately assess or monitor the pollutants in polluted soils. Because of time paucity, I cannot elaborate these techniques, how we can apply this soil solution extraction, but from the picture actually, these images can give you an idea how we extract soil solution in situ. This is actually in situ, example of in situ condition where you can extract soil solution from growing crops actually, from soil under say under crops where maximum vegetative stage actually reach. When it reach, then you can extract the soil solution with the help of some little instrument. This is called rhizome sampling, and you can install this thing in pot as well as in field conditions. Okay, so by that you can extract the soil solution and you can analyze it for different metal and metalloids. Now these are examples because I already discussed about say DTPA, EDTA, calcium chloride, sodium nitrate, ammonium nitrate, sodium bicarbonate, and sodium bicarbonate is mainly for your arsenic extraction. This salt, sodium bicarbonate, also an extractant. This is actually also an extractant, can also the same procedure actually used for your extraction of your arsenic. Okay, for extractable arsenic, to represent the extractable arsenic, sodium bicarbonate can be used. Now, these are actually instruments that can be used for your precise estimation of your trace toxic elements or metals or metalloids. Few examples for students, this is of your interest, that you know atomic absorption spectrophotometer, and another instrument that can also be used like inductively coupled plasma mass spectrometer, or optical emission spectrometer, or atomic emission spectrometer, that can also be used for accurate determination of your heavy metals or metalloids. Now, maximum allowable limit, this is very important for heavy metals in soil as used in different countries, but it has some limitation, as I have already made mention that total metal will not account you the actual damage towards the human health as well as your animal health, as well as your, it will not reflect towards plant uptake also. So total metal, it does not carry any significance or any meaning, but still we should know that what are the different stringent limits that actually used by different countries. In India actually we generally follow the Great Britain, the limit proposed by Great Britain. For arsenic, the critical limit is actually total arsenic. It's 10 to 20 ppm. For chromium, it is 50 ppm. For cadmium, it is 3 ppm. For zinc, it is 300 ppm. And for lead, it is 100 ppm. So in India, actually, we follow this limit as prescribed by Great Britain. Okay. Now, how we can, because now we are actually talking about monitoring or assessing the polluted soil. So this is very simple. This is first first technique, you can note down the first technique of assessment is actually comparing the total metal. Okay, if you have say polluted soil and you can extract the total metal using say acid digestion, you can take the reading also with the help of either ICP-MS or AAS, and whatever results you are getting, you can compare with these values, whether your total lead actually exceeding 100 ppm or not. If it exceeds, then you will call that soil as polluted soil, and if your limit is say lead value you are getting say below 100, then you can say that it is not polluted. Okay, here also, from here also you can coin your soil as whether it is polluted or contaminated. If it is above this total critical value, then your soil will be termed as polluted soils. Okay, so this is one way of assessing. If it exceeds the say total limit, then you will recommend the particular farmers that your soil is polluted, so you should take some intervention. So this is first technique. Okay, first technique. Second is actually permissible limit of metal and metalloid content in food materials. So first technique, it was like in soil, and the second technique is actually related to your plant. Whatever plant material, whatever food, whatever crops you are growing in that particular soil, you should judge whether the level of that particular heavy metals or metalloids, whether that is within the permissible limit or not. Okay, here are few examples of say cadmium content in rice. Okay, different countries they have proposed. So for polished rice it is for China 0.4 ppm, for Japan it is 1 ppm. This is another example of DOH 0.5 ppm. So these are few limits actually. This is actually based on your plant material content. Okay, content of your heavy metals or metalloids in plant material. Now, if you have the plant samples, you can estimate the total trace toxic elements with the help of digestion. Again, digestion of your plant material with nitric acid or any other acids like your diacid or triacid mixtures. Then you can estimate your target metalloids, and you can compare whether your results is actually exceeding the prescribed limit or not, and accordingly you can communicate to the farmers, and you can interpret that this soil, okay, because ultimately the element is coming from soil towards the food crop. Okay, so you can recommend your farmers that this soil is actually unsafe for growing your rice crop or any other food crop, because here actually mostly these limits are mainly prescribed for rice or other cereals. Okay, you can see here that in crops also these limits actually not standardized. Okay, in crops also these limits are not standardized, so only for rice it is available, but for other elements, other metals, what will happen? So this is for rice actually it is standardized. Okay, this is another limitation of comparing metal content in food materials. This is second technique. Okay, first technique is based on total metal content in soil. This one, first technique is total metal content in soil. Second technique is based on metal content, metal or metalloid content in food material. Based on this also you can assess the soil as well as your crop, whether that is fit for consumption or not, that you can assess. Third is actually using drinking water limits. These are very important. So you can otherwise I can give you this material also after this lecture. I will share the PPT. These limits are very important because in every competitive exam you may face questions like what is the permissible limit of arsenic in drinking water? You should answer like 10 ppb. 10 ppb is the permissible limit of arsenic in drinking water. Okay, so these limits you can also compare in your irrigation, in your drinking water, because I have not given the irrigation water limits here, because in irrigation water there are for all elements, the limits actually so far have not prescribed. Say for arsenic, one limits actually we know one limit for arsenic is there, that is your 100 ppb. For irrigation water it is 100 ppb, and for drinking water it is 10 ppb. Okay, so we can compare this limit of your drinking water, obviously after estimation of your drinking water for particular target element, and you can compare whether that water is safe for consumption or not. Okay. Now, next technique is actually risk assessment with the help of hazard quotient calculation. This is actually non-cancer risk assessment. And another technique actually recently we have used, the cancer risk assessment, where you can calculate the cancer risk of particular soil, and you can say that this soil how much safe it is to go for cultivation or not. But this non-cancer risk assessment, actually the protocol was proposed by USEPA, United States Environmental Protection Agency, and they have given this formula HQ, hazard quotient. It is actually average daily dose divided by reference dose. Average dose divided by reference dose. And more elaborately, when we calculate HQ like M plant multiplied with the daily intake of the food materials, and again you have to multiply with the conversion factor to get the average daily dose. This is very simple method. So for calculating hazard quotient, what you need? For calculating hazard quotient, you need the metal or metalloid content in your food material or your plant material. That you can do with the help of acid digestion followed by estimation with the help of either atomic absorption spectrophotometer or inductively coupled plasma mass spectrometer, ICP-MS, ICP-OES, whatever. So you should have the data of your metal content or metalloid content in your plant material. Okay, and this hazard quotient you can, now people are actually researchers, they try to recommend the hazard quotient value not only for your, you can classify it HQ for children, HQ for adult, HQ for again among the adult you can classify for girls as well as boys. What would be the different value of HQ? Because one factor will here vary, like here I have multiplied RFD into 68. 68 is actually average body weight. Okay, so this body weight that can vary. For a small child the body weight will be less. Okay, for a lady weight may be less. So for different category hazard quotient can be calculated. For more details, my contact number you can take, or my email ID. I can guide you in detail that how we can calculate hazard quotient. This is actually non-cancer, because I am not presenting cancer risk assessment. Recently we have published one article where we have presented that cancer risk of people actually residing in Asian region, particularly in Asian region where arsenic problem is most prevalent in Asian region. Okay, for that I can guide you. Okay, you can contact. These are actually reference dose that can be used for calculation of your hazard quotient, because RFD value you should put here. So already RFD values are prescribed by USEPA. So these are the RFD values that you have to use while calculating the non-cancer risk assessment in terms of hazard quotient. Okay. This is the last technique that risk assessment or the monitoring. In other words, because we are talking about the assessment or the monitoring of the polluted soils. So this is actually the modeling framework where we actually integrated few things: metal solubility, metal or metalloid solubility in soils. They are transferred to plant and ultimately to the uptake or say consumption by your human being, consumption of your food material, metal contaminated food material by human being, and that can be integrated. This whole thing can be integrated, and we can prescribe the, our ultimate motto is actually prescribe the safe limit of your extractable metal, and that is based on or in relation to human health. We can say in relation to human health, we are actually prescribing the safe level of heavy metals or metalloids. So this is our contribution. This is more advanced, where we integrated all these three aspects: your soil aspect, that is metal solubility, then second part your plant uptake, that also can be done through modeling approach, and third is actually assessment of risk to the consumers. Okay. Now, one example actually I'll show you here, that we have conducted this study in Malda district, where arsenic problem we have seen with the help of medical team, and we have identified mostly 4 blocks: Kaliachok 1, Kaliachok 2, Kaliachok 3 and English Bazar in Malda district of West Bengal. And we have identified that these are the diseases. These are chronic arsenic toxicity. Okay, pigmentation and keratosis. You can see the level of the disease burden among the residents residing in that particular area of Malda district of West Bengal. Other examples also, disease outcome I have listed. These are another close photograph. Pigmentation, this is called keratosis. Keratosis, it is actually, you see this keratosis, it should be always in either your in hand. Pigmentation, it is in your body trunk, that brown pigmentation. Okay, pigmentation body and limb. So these are actually outbreak or the effect of your chronic arsenic exposure, either through your drinking water or your food materials, mostly rice. Rice, it always has some preferential uptake for your arsenic, and that's why the problem we have identified in that particular area. Because in West Bengal, the major diet preference is actually rice. Rice every 3 times in a single day. But in say north belt, particularly here, you see Rajasthan, Punjab, here people used to take chapati, roti, not that much rice. But we Bengalis from West Bengal are very much fond of your rice intake. 3 times in a single day. Okay, so 400 gram, 500 gram rice we used to take. That is another reason of your arsenic problem. So much rice consumption. Okay, so these are some data. Actually, I will not give you the detailed account, because we have identified the cases also. Cases means the problem, arsenic problem we have seen in these 50 people, 24 people, 3 people, keratosis, 30 people, 10 people. These are identified persons. So now this is another important table, exposure route. You see drinking water and raw rice grain, where actually we have seen that that minimum maximum you can compare cases and controls. You can compare arsenic concentration in drinking water, where we have identified the cases like your arsenic problem in people. We have seen the higher concentration of your arsenic. They are consuming higher concentration of consuming drinking water containing higher concentration of arsenic as compared to controls, where we have not seen any kind of disease. Similarly, with rice grain, you see in raw rice grain, what actually we collected from patients' household, we have seen higher concentration of your arsenic in raw rice grain as compared to your control household. Okay. Now, these are actually some soil physiochemical characteristics in that experimental soil of Malda district. We have seen that higher concentration of Olsen extractable arsenic as well as total arsenic as 7.21 and 233 ppb of Olsen extractable arsenic in that particular 4 areas. Okay. Now, this is actually predicting the uptake of arsenic using the model. I will not give you the detail of this model. So there is one model actually we have standardized and for prediction of your metal or metalloid uptake. Okay, for prediction of your metal and metalloid uptake. So from R square value, we can see that this model can be successfully used for prediction of your metal uptake. The hazard quotient concept actually I have already discussed. So you can see that the HQ actually it exceeds in few cases of 1. Value of 1 is actually the permissible limit. HQ value it should be always less than 1. So once it exceeds 1, that means the food material is unsafe for consumption. So in this Malda district actually we have calculated hazard quotient and we have seen that particularly for rice grain the HQ value exceeded 1. Okay, but for other crops it is within the permissible limit. So rice, again it is proved that rice has preferential uptake of arsenic. In Malda district we have proved this theory. Now this is the safe limit. What actually our contribution is, we have established the safe limit of your extractable arsenic in that particular region with respect to rice crop. And here we are actually recommending that 0.43 ppm of arsenic is actually safe when soil pH and organic carbon content are 7.5 and 0.5%. Another limits actually we are actually proposing as 0.54 ppm when pH of soil 8.5 and organic carbon 0.75%. So these are actually arbitrary combinations. These are if the condition exists like this pH 8.5 organic carbon 0.75 then the limit would be 0.54. Okay. So you see one typical characteristics that when carbon content we are increasing 0.5 to 0.75 then your extractable arsenic limit is also increasing 0.43 to 0.54. So what does it mean? When you increase the organic carbon, your limit is also increasing. So it actually signifies that organic carbon, if you can increase the content of your organic carbon, then that can actually hold or that can bind the trace toxic elements, not only arsenic. Okay, so what actually I was discussing then for 10 years we are actually maintaining one field experiments applying sludge in soil, how best we can use sludge in agriculture. We have seen that that the metals, whatever metals we are estimating, the metals actually not transferring from soil to plant because sludge also contains higher quantity of your organic matter. So organic matter will hold your trace toxic elements. Okay, I think the students they can have better insights that how this carbon content is actually playing a key role. 0.43 to 0.54. So 0.11, almost 0.11 unit actually you would be safe. So you have more expansion of your limits. Okay. These are actually already I have discussed that HQ. One more important thing I forgot. HQ you can calculate not only for your food material. Hazard quotient can be also calculated that other route of exposure like say through soil. Soil also we are taking. Okay, children's they used to take soil. Then your inhalation. Then your other diets, water. So these are other source of exposure. Okay. So that's why we have sometimes we have kept the kept our hazard quotient limit as not 1, rather than it is 0.25. In some cases, it is 0.5, the safe limit of HQ, because we are considering only one route, our food material. But there are other routes also, routes of exposure. Okay, inhalation, drinking water, soil ingestion, these are other routes. So you should be very much careful while using this HQ concept, that what should be the critical limit of HQ. Okay, in our paper also you will see that HQ we have kept as safe, sometimes 0.5, sometimes 0.25 also. Now quickly remediation, because time I think it's already 1 hour. Some approaches we have used so far for remediating the polluted soil. For students, actually, you all know these are the different techniques of phytoremediation. Phytoremediation means using plant you can remediate your contaminated soils. So these are a typical example of different plant species through which actually you can remediate your target elements, particularly say arsenic, Teres vittata, Chinese break fern, that can be used. Say lead, cadmium, here you can use mustard crop, mustard. We have so far we have used mustard, then some few your marigold, mustard, marigold, then spinach, then amaranthus, then bathua. These are actually crops that can be used for your remediating your polluted soils. This is important slides, that these are the materials and that can be used. Other than your plant, some inorganic material also can be used. And in our research, actually, particularly with respect to arsenic, we have used both inorganic as well as organic materials like your farmyard manure, vermicompost, then your rice husk, sugarcane bagasse for immobilizing arsenic. Okay. This one I will not talk, because radish, sunflower and mustard, this study was from Dr. S.P. Datta. Yeah, this one actually I will talk because I was also involved in this work. That co-application of silicate and low arsenic accumulating rice cultivars, that integrated use of silicate as well as your some low arsenic accumulating variety that can be used combinedly to arrest the arsenic transfer from soil to plant, particularly rice crop. And here you can see that hazard quotient value, it can go below 0.5. Okay, I was talking that safe limit of HQ, sometimes we kept at 0.25, sometimes 0.5. So here actually in this study we kept 0.5 because we are actually calculating the HQ only through one route, our food materials. Okay, there may be other routes of exposure. So with the help of using this silicate as well as this variety, okay, this Badshah Bhog, another example of your rice variety, we have seen that Badshah Bhog variety, it's preferential, low uptake, okay, low accumulation. So you can use in combinations using silicate as well as your low accumulating cultivars. Another example of your irrigation management, you know, now we are actually promoting that less use of water in rice cultivation, particularly in say direct seeded diet, okay, or say upland rice crop where less use of water, or alternate wetting drying. This concept actually came from alternate wetting drying concept, where we have seen if you integrate alternate wetting drying along with your phosphate or vermicompost application, then your arsenic can be arrested. It will not transfer from soil to plant. We have seen that. Another example, it's Bihar. What I was talking, that in Bihar also we have worked on some arsenic management, particularly in field. Field also we have used. In field experiment, we have used rice straw, then your farmyard manure, vermicompost, sugarcane bagasse and paddy husk. And we have seen that the sugarcane bagasse and paddy husk, these two actually, this is marked actually. So these two material, sugarcane bagasse and paddy husk, can be effectively used for your arresting arsenic, particularly in soil. Now, another example of modeling, and here also we use some concept of your organoarsenic complex, how we can assess the equilibria. And here also we have used some organic matter for assessing as well as fitting our model. The name of the model actually is solubility free and activity model. That model actually we have used for fixing the safe limit. Okay. And another work actually we have done for developing some extractant, and this is I think of not this is another example of setting the safe limit of your arsenic in soil, but by using your machine learning algorithm, artificial intelligence, and this is the area of artificial intelligence and machine learning. So we have set the limit by using so many samples we have used, particularly collected from West Bengal, and we have determined the bioavailable arsenic threshold as 14 ppm. 14 ppm we have seen as well as 11.75 ppm by logistic regression. So these two limits also very important while deciding your land, whether the land is suitable for cultivation or not. That will give you a good picture. So let me conclude my talk that the precise in future what we can do. Another fast research area what I understand one should take immediately, that mapping of your polluted area. Mapping of your polluted area. What is the area, actual area? Because our research is actually in discrete area, this district, this block, this village. Okay, but if we can map with the help of either NBSS LOP or your Soil Survey of India, that would be of great value. Then there is urgent needs for developing standards, in that area actually we are working development of standards. We have already started, like as I already presented, that we have established the safe limit of extractable arsenic. Similarly, for other heavy metals also, we can apply the same knowledge. In this way, we can go for safe limit of extractable heavy metals like cadmium, lead, all we can establish. Then rationalization of safe value of HQ, that already I discussed, that sometimes we are actually keeping the HQ value as 0.25, sometimes 0.5. So this rationalization of HQ value is required because why it is important? Because the food habit is not equal. Already I have made mention that West Bengal people, they will consume more rice. Punjab people, they will consume more chapati, more roti. So there is a conflict. So we need to rationalize this hazard quotient value. Then determination of relative arsenic uptake efficiency in different plant species, because this lead actually we got from that arsenic uptake is preferential, and it is mostly taken up by rice crop, not other crops. So plant species wise data we actually need. Then distribution of arsenic in different plant parts, speciation of arsenic in different edible portion of crop is required, and development of comprehensive reclamation packages required, and some artificial intelligence and machine learning. That in this area actually we have recently started that application of machine learning, how best we can use machine learning for protecting the human health. Thank you so much. Now I think we can go for question
बहुत
and
बेहतरीन लेक्चर रहा सर का, बहुत अच्छी तरीके से एक एक चीज को उन्होंने समझाया। अगर कोई भी पार्टिसिपेंट्स, कोई भी स्टूडेंट इस पर्टिकुलर पीपीटी से रिलेटेड कोई कुछ बात करना चाहता है, कोई किसी का डाउट है, तो वो 1 to 1 अनम्यूट करके अपने आप को सर से बात कर सकते हैं। 5 मिनट का डाउट क्लियरिंग सेशन है सभी पार्टिसिपेंट्स।
Good evening, sir. मेरा नाम किशन राज है। मैं विश्व भारती शांति निकेतन का छात्र हूँ। तो सर मेरा एक क्वेश्चन था, जैसे सॉइल प्लांट वगैरह में तो हम लोग सॉइल साइंस वगैरह पढ़ते हैं, तो उसके बारे में चेक वगैरह करना, उसका क्या लिमिट है वो तो पता चल जाएगा। बट अगर हम रिसर्च करना चाहते हैं ह्यूमन के ऊपर कि इस तीनों को कोरिलेट करके, जो आप लास्ट कंक्लूजन वाला स्लाइड में था ना, सॉइल प्लांट और ह्यूमन वाला, तो वो कैसे कर सकते हैं, इस पे थोड़ा सा आप बताते हैं, क्योंकि मैं इस पे थोड़ा रिसर्च करना चाहता हूँ।
Exactly. So soil, plant as well as human, if you want to include in your research, then you should first identify a particular area that these are the villages I will cover. Okay. Then you have to go for your sample collection, like your this is called actually paired sampling. Paired sampling. You have to take soil sample as well as your plant sample. In that soil, whatever plant is actually growing by that farmers, so you have to collect paired sample in that particular area. Now to include human in your subject, so you should go for biomarker collection. What actually we have tried to collect some biomarkers in affected areas. Say for example, say Malda district, we have identified that these are the people already affected. So you can go for biomarker collection from that area, from where you are collecting your soil plant as well as your human sample. What are those biomarkers? Biomarkers means human sample, mainly your urine or say nails or hair. These three are actually biomarkers: urine, nail, and hair. So if you can collect, or blood serum, also another example, but blood serum will not always reflect your arsenic problem. Blood serum can be used for your other trace toxic elements, zinc, say cadmium, say lead, that you can collect for heavy metals. But for arsenic, these are three biomarkers: nail, hair, and urine. So if you have the provision of your in your institute that you can collaborate with some say medical agency or say medical people where this ethical permission is required for collection of any human sample. So just go for particular area, take small area, affected area where reports are there and problems are already there in human body, and then you can correlate your soil data, plant data, ultimately your human data also. So I have one research paper I can share where actually we have correlated the disease burden, how it is related with your arsenic content in your rice grain or arsenic content in your drinking water. So you have to collaborate with some medical people to include the human component. Otherwise, you can go for this calculation, this hazard quotient calculation, then your cancer risk calculation. That is actually indirect way of including human health in your study. And that way also you can say that this is soil, plant, human continuum. If you calculate hazard quotient you can calculate. Already I told you how you will calculate hazard quotient. Okay. I think for more you can, I have given my phone number also. You can contact me also over phone.
सर
Any other?
सर जैसे एनर्जी रूल होता है फूड चेन में 10% वाला, तो क्या इस तरीके से हम लोग कोरिलेट कर सकते हैं कि ह्यूमन में, मतलब ये वाला तीनों में कुछ कोरिलेशन होता होगा?
नहीं
मतलब
ऐसा नहीं, तीनों का कोरिलेशन अभी जो हम लोग ने जो देखा है कि आपका जो जैसे हमने बताया पेशेंट्स का जो सॉयल या प्लांट मटेरियल जो फूड ग्रेन हमने लिया था उसमें देखा था कि ज्यादा है लेवल एज कॉम्पेयर टू जो कंट्रोल जो था हमारा स्टडी में। तो ये कोरिलेशन है, ऐसा कुछ ऐसा कोरिलेशन है नहीं। ओके, एज सच ऐसा कोरिलेशन कुछ है नहीं, बट यू कैन एक्सपेक्ट दैट जहाँ पे पेशेंट से जहाँ पे प्रॉब्लम है, ह्यूमन में प्रॉब्लम है, उनके घर का जो आपका ड्रिंकिंग वाटर है या आपका उनका फूड मटेरियल जो है वो दैट कैन हैव मोर कॉन्सेंट्रेशन ऑफ आर्सेनिक, ये कोरिलेशन हो सकता है. So many questions I can see. Thank you. One by one I can give if time permits, then Uttam Hole, how does soil pH affect the availability and mobility of toxic elements? Yeah, soil pH it can affect, because with increasing pH actually availability of any trace toxic elements is actually decrease. Okay, say in alkaline soil your availability of your trace toxic elements will be automatically less as compared to your acidic condition. When pH is less, the availability will also more. Okay, then next question is how hard material present in soil affected on crop yield? How hard material present, I think toxic material present in soil affected on crop yield? Yeah, we have seen particularly in Debari soil, where we have seen that zinc smelter effluent irrigated soil. They are actually we collected soil samples from there, and we conducted pot experiment with wheat crop and your spinach crop in our pot experiments, and we have not we have not seen any kind of yield there. So yield, crop growth was actually ultimately affected, not to the fullest, not to the ultimate potential. We have not seen any kind of yield there. The highest polluted soil. Another example, please give your mobile number. I have already given. Can you share PPT? I will share this PPT, okay, to the organizer. Very informative. What should be the phenology of the crop in saline soils? Okay, saline soils. We have not seen any metal toxicity or presence of trace toxic elements in saline soils. So this one I cannot answer, the phenology of crops. But for say Debari soils or Sonipat soils, where cycle factory effluents irrigation was for last say 10 decades, we have last 3 decades we have people actually used that effluents. That soil, the phenology is like we have not seen any kind of crop growth, full growth. Yield was also not up to the mark in that particular soil. Yeah, I have not seen any more question in the chat box. Yeah, any more questions?
डॉक्टर साहब बहुत बहुत धन्यवाद आपका कि मेरे रिक्वेस्ट पे आपने अपनी व्यस्तता से समय निकाल के
हाँ,
इस वर्कशॉप में अपना लेक्चर डिलीवर किया, और आगे भी इस तरीके का सहयोग आपका बना रहेगा ऐसी उम्मीद करते हैं. हम एक 20-21 फरवरी में चंडीगढ़ सेक्रेटरिएट में एक 7th ग्लोबल एग्रीकल्चर कॉन्फ्रेंस भी प्लान कर रहे हैं, जिसका ब्रोशर मैं आपको भेजूंगा. यदि आपकी अवेलेबिलिटी रहे तो आप जरूर आइएगा.
ओके ओके, श्योर श्योर श्योर.
बहुत बहुत धन्यवाद डॉक्टर साहब. थैंक यू सो मच.
ओके ओके, थैंक यू सो मच. थैंक यू.
सभी पार्टिसिपेंट्स लीव कर सकते हैं. सभी को गुड नाइट. जय श्री राम.
ओके, थैंक यू.